Okie dokie. The frequency of a Wi-Fi is 2.4 gigahertz. Giga is 9. And the speed is the speed of light, which is 3 times 10 to the 8 meters per second. Or it's actually, what's it like, 2.997, if you want to be. Isn't it something like this? I actually think C is on your calculators already. It's one of the constants. Do you have constants on your calculators? It's like C0 or something? No? You have it on yours, Matt?
Yes.
What number is it on yours? 28. You don't have it on yours? No, okay. Yeah. Anyways, what am I asking you for? What is the wavelength? So lambda equals C over F, which is the speed of light, over 2.4 times 10 to the 9 gigahertz. That's gigahertz. Shift 7, it's constant 28, you said, Matt? See, there it is on my calculator. So that's really handy. Over 2.4 times 10 to the power of 9. Did you get this? 12 and a half centimeters about. Okay, good stuff for you. Matt, how did you get terra on your calculator? What did you press? Shift 9. No. Not on mine, I guess. Oh well. Okay, number 2. What type of wave is one with that frequency? Now you can actually see it on my chart. It's 5.45 times 10 to the 14. So what is that? 5.45 times 10 to the 14. So that's halfway between 10 to the 14 and 10 to the 15. So that's visible light. Can you see it in my picture I provided? Yeah. You see I gave you you can look it up in the picture. So that is around about the visible light. So, visible light. Did you calculate? Yeah. Spelled what wrong? Did I? What did I spell? Oh, visible. Yeah, thank you. Don't worry, in the exam I'd still give you the mark. Because visible, is that a word? Viable's a word. Okay. A visible light wave is given more energy and its frequency increases. At what frequency will it become invisible? So when can you not see the light? When its frequency becomes so high it changes colours. What's the last colour you can see? Purple, also called violet. And then the colour above that you can't see. And what's that colour called? Ultraviolet. Now you can actually look at it in the picture here. Where does ultraviolet begin? Around about 10 to the 15, roughly. 10 to the 15 hertz. Yeah? I'd say about 10 to 15. By the way, I forgot to tell you this last time. Humans can't see ultraviolet. The last colour we can see is violet. But birds can see ultraviolet. Did you know this? So some birds can see this colour, ultraviolet. It's kind of like how Siva could hear the mosquito sound, but we couldn't. Similar idea. So the birds can see the higher frequency colour of ultraviolet that we can't see.
Are these humans can see ultraviolet?
Not that I know. Not that I know. I've never heard of this happening, but I wouldn't think it's. Would it be impossible? I'm not sure. Maybe I'll Google it later to see if anyone has. Of course, ultraviolet is, you can't describe what colour it is because you can't see this colour. But what's interesting is that your nails and your hair, they reflect ultraviolet from the sun. So if a bird was looking at you, your hair and your nails it wouldn't look like the colour it looks now. It would look a different colour because it would look ultraviolet because it's being reflected, you know. So the reason birds can see ultraviolet is so that they can always see where the sun is even when it's cloudy, because they can see the colours in the sky. So they get a sense of which way east and west is, you know. So this is the reason why. Number 4. EM waves with frequency equal to or greater than UV are harmful to humans. These waves are well known to cause cancer. Are waves from mobile phones harmful in this way? No. Short answer. Because its frequency is too low. What's the frequency of mobile phones? Do I have it on that picture? No, I don't. It's somewhere around about microwave, so about 10 to the 9. That's much less than the 10 to the 15 when it becomes dangerous. Much less. Like the difference between 10 to the 9 and 10 to the 15 is 10 to the 6, which is 1 million. 5. With the help of the diagram below, answer the following. What kind of electromagnetic wavelength has the shortest wavelength and the longest? So which has the shortest wavelength? That is gamma. Gamma, and the longest? Radio. In particular, AM radio. Okay. So gamma and AM. What kind of electromagnetic radiation could be used to see molecules and a cold virus?
Infrared.
Yeah, good. Yeah. So, let me explain something here. Obviously, you can't see very, very small things with your eyes, but if you use a microscope, you can see very, very small things. But there's a limit to how small you can look at something, and the reason for this is because of the light. You can't look at anything that's smaller than the wavelength of the light that you're using. Okay, because I'll try and draw a picture. So, like, say you're looking at something here under a microscope, something that looks like this. So, if the wavelength is quite small, it will come in, it'll hit off it, and it'll go into your eye. But if the wavelength is quite big, when it hits off this and bounces off, you can't get all this little detail because it's hidden by the wavelength. The wavelength is too big to pick it up. You get what I'm saying? It's like it's not fine enough to see the detail. So you can see smaller things if you use smaller wavelengths. But then there's a problem. If you use small wavelengths, then you can't see the light because your eyes can't see past red and violet. So what happens is you use a small wavelength, you use a computer, the computer takes the image and then converts it into something that you can see. So by using different wavelengths and a computer, you can see different levels of details. So if you want to see something really, really small, like what did I ask you? A molecule. What's a molecule on the picture? Like a water molecule, you have to use something like an X-ray. Something like an X-ray. If you wanted to see something like a cold virus, you would have to use something like a... You could use infrared. But you can just use normal visible light. You just need the wavelength to be small enough, but it could be smaller. So actually, to see it, you could just use visible light for the second one. So the answer is you must use at least X-ray and also visible light you can use for the cold virus. But for the X-ray you would need for the molecule. Yeah? Is that okay? This makes sense. You know, if you looked under a microscope, you could see a virus under a microscope with just normal light from the light bulb. But you could never use a microscope and a light bulb to see a water molecule. Yeah? It's okay, Matt? You look confused. No, ask. You have thoughts.
So they don't have the exact shape of the molecule.
You could see the exact shape if you use something like an X-ray. Or a gamma ray, maybe. Yeah. Yeah. Question? What's up, guys? Question? Akuma, what's your question? Are you sure? Alright. Why can't you use visible light to see a molecule? So what's the reason?
Too small.
What's too small exactly? The what? No, you have it the wrong way around. The wavelength's too big. You need it to be small enough. Basically the rule is this: the smaller the wavelength, the more details you can see. If you want to see, you know what, it's like on your phone. You know, you have, the picture has a resolution. The more pixels, the better the image, right? You know, 1 megapixel, 2 megapixels, 2 megapixels makes a sharper image. Same idea. The smaller the wavelength, the more resolution, the higher details you can see. So the reason you can't is that the wavelength is too big. You want the wavelength to be less than the size of the molecule, at least. So for example, if the molecule is 10 to the minus 10 meters, for example, the wavelength must be smaller than this. And the smaller the better. Yeah? Okay, and the last one, I actually already gave you the answer. Some insects like bees can see light of shorter wavelength than humans. What kind of radiation do you think a bee can see? So the bee can see the ultraviolet, like the bird. And again, you can understand why the bee would need to see the ultraviolet, because the bee would need to know where the sun is to get a sense of direction. You know, so if the bee leaves the hive in the morning, the sun is in the east, and when it comes back in the evening, the sun is in the west, so it's in an opposite direction. You get the idea? Like north, south, east and west. So we'll keep it simple. Suppose the bee builds its hive here. When it leaves in the morning, the sun will look like it's behind it. And then in the evening when it sets, it should travel so that the sun is still behind it. So in other words, it's travelling so the sun is always behind it, as an example. You know. And this is great for the bee because it works even when it's cloudy. So what will happen is, when it's cloudy and the sun's behind it, we can't see it. But the ultraviolet can still come through the clouds. It's just we don't see it because we don't see ultraviolet. But the bee can see it. So it's very useful. Okay. Right, we'll close that and we'll go to the lecture now.